Hello everyone, my name is Anand Raj. I'm a product manager on the Network Services platform, and I'm here to talk about a specific application called IP and MPLS optimization. This application is basically a PCE. It also does resource controlling. So the two main things that this application does are path computation, optimization, and resource control. So what I'm going to show you today is a specific use case which service providers may be interested in. And what it does is it really does inter-domain path computation. So what you see here is a Network Services Platform login page, and there's a plethora of applications available here. We're going into our IP MPLS optimization application, but prior to that, let me show you a little bit on the slides on what the application is. So the NSP IP MPLS optimization application provides centralized SDN control across inter-domains. And what we'll show you is how the NRCP computes a path end-to-end with intelligent path computation and while optimally allocating resources. So the key thing is you want to maximize path optimization while administering and scaling routing domains the way you want. The challenge today is we have lack of inter-domain coordination. So while you have multiple domains in your network, in order to be able to successfully route a path across these domains, you need to distribute routing and control information across these domains. And that may be a challenge for some of the devices in the network as the amount of control plane information can quickly scale up. So what the NRCP does is, first thing, it provides visibility into these domains. And it also provides an ability for the operator to realize that these prefixes or these IP addresses are reachable within the domain itself. And from that point on, it simply goes along and computes the best path across the domains. So the NSP provides centralized control by supporting multiple instances, even on the same routers. So we'll see in our application, as I switch to my web client there, and how the NSP discovers the different domains, how it interlays the domains on top of the common routers, and how it calculates a path. So one quick thing is we support both technologies, which is creating paths via RSVP, which is a technology that's in use in service providers today. We also support segment routing, which is a new and upcoming technology and which is quite scalable. However, one of the challenges in segment routing is the ability to contain the information with a few segment routed labels, and that's why we have something called the max SID depth problem. While you're spanning across IGP domains, if you're spanning across multiple routers in the multiple domains, it's almost impossible to supply an ERO with as many labels as you want. Therefore, we have some optimization techniques that we will showcase, primarily how we can reduce the ERO across these multiple domains. So the solution is really to provide centralized control, and also if you have the ability to specify any cast as segment routed labels for your border points, as shown in this diagram here. So in this diagram, we've got a 3-domain network. You've got any cast representation on the border points between instance 1 and instance 0, which are really 2 routed domains. And you've got any cast representation between instance 1 and instance 2. So what we do is, while we can optimally calculate a path across these domains, we can only specify if you want to contain the segment routed label stack to the only any cast segment representations. So we offer 2 solutions in the space. The solution 1 is you can specify loose hop any cast ASBRs if they're present. And solution 2 is you can specify loose hop ASBRs. The difference between the 2 options is that if any cast is available, the NSP takes advantage of the presence of any cast labels and computes a path using any cast labels. In the second option, if any cast labels aren't available, then we specify simply the best border router to reach from one domain to the other domains, and therefore our ERO specification is really a list of the most optimal border routers. Mind you, the NSP does in fact calculate the best path because it simply does a graph computation from the source to destination across these multiple domains. This is simply possible because we are able to discover all the domains, we're able to discover the interconnection points, and we're also able to discover all the reachabilities. So when we specify the exact, or when we pick the exact path we then realize how to best specify the path using what's available to us. So that's why in option 1, you've got any CAS SIDs, we use any CAS SIDs. In option 2, where you don't have any CAS capabilities, we specify the border routers. Now, between solution 1 and 2, there is a fallback mechanism. If, for example, you cannot determine the ideal pair of any cast, or if there any cast information isn't available, we automatically fall back to option number 2. And that's what we'll showcase today. So here we have the NSP IP MPLS optimization application. As you can see, there is a map pane here, and you've got your list of LSPs that are currently available in the system. The application also lists all the current IP addresses and the reachabilities. So let's go and see all the domains it's connected to. Okay, so if I click on all, you can see that there's about 3 domains here, and the way these domains are shown is simply by the link colors. If you want to understand what these domains are, you can actually drop the list down here to see the different topology IDs that we're getting. All the network discovery that's done here is done via BGPLS, and therefore you will see that the topology ID is based on the BGPLS parameters. So you have the IGP instance ID, AS number, and the BGPLS identifier that uniquely discovers these domains. Now, since these domains are on multiple routers, you can see that this common ASBR router supports domain number 10 and 20, and this ASBR router supports domain 20 and 30. If you want to look at the level of any CAS SIDs, you'd have to look at some of these routers on which the any CAS SIDs are advertised. So, for example, on this ASBR, which has a router ID of 38.120.48.221, if I specify all the prefixes or prefixes that I'm advertising from this router, you can see that I have a bunch of Anycast prefixes that I'm generating. Okay, this specifically here, the 20221, is an Anycast prefix that's generated by this router here. So if I go and specify just the Anycast prefix, and if I search on that, so you look at the Anycast prefix 200200 that advertise from both routers 221 and 223. And that's how you can indicate if it's an Anycast SID. Okay. Now we'll go back to a list of LSPs. And the first thing we'll try and do is we'll basically connect a path all the way from the domain on the left to the domain on the right. So as you can see, these are multiple ISS domains. And because the reachability is contained in each of these domains, Node 219, if it needs to generate a path or connect a path across these domains, can only do so by informing or by connecting to its next hop router. So because the NSP learns all the prefixes and reachabilities, it is easily able to connect a path from end to end. We'll see how. Okay, so let's go on the CLI to connect an LSP. As you can see, there's 2 LSPs here. Each of the LSPs actually start from Las Vegas 219, which is shown in the domain on the west, and they traverse across domain 20, and it terminate on this domain. I'm just increasing the size here. That's 190 there. So if you look at the definition of the LSP, you have a destination address specified, the wording CSPF. There's PC computation, PC report, enable, and control. These are simply PC options to determine the amount of control that the PCC client needs to award for that LSP to the NRCP. So PC computation instructs the NSP, that to compute a path. The PC report here reports the state of the LSP once the NSP provides a PC path. And the PC control here instructs the NSP to be able to control the LSP should it need to reroute. Now, one different thing that you'll see here, which is path profile 20, this is specified and has no particular significant meaning on the PCC. It's just a number that's added here. This path profile, however, has significance on the NSP. So I'm going to simply unshut this LSP. So now if I go onto my NSP, you can see that this LSP is now up and is routed. So it's segment routed type. Its operational status is up. It starts from 219, ends in 190. So if you now look at the actual highlight of the LSP, what you'll see here is you'll see a bunch of routers that are highlighted and not the paths. Okay, so we'll check out the highlight again. Close the controls here. So essentially what this means is that if a path is transiting from 2.1, or path is originating from 2.19, its transit points are potentially 198, 199, and 221, 223 across the two domains to get to the destination, which is 190. So we're transiting through various domains, and we're picking the best Anycast pair here. And to get details of the Anycast pair, you just drop down the LSP, and you'll see the ERO specification here, okay, which is basically an Anycast SID. Okay. If I expand this link here just to show you a little more detail, you can see that the original SID is simply an Anycast as well. So both these routers here, 198 and 199, which are the transit ASBRs, provide an Anycast SID in terms of distribution into this particular domain. So that's the first ERO specified. 221 and 223, as you saw before, provide 200, into this domain. These Anycast SIDs are only sent within this domain. So 200, which also has an Anycast IP address, is not sent to the first domain. And that's a key thing. So in the ERO specification, you can see how you've got the first Anycast SID, the second Anycast SID, and the destination. Okay? That's how the NSP provides the ERO across domains to enable path computation across domains. Obviously, in this situation, because we're supplying the Anycast SIDs as EROs, the actual path is not known. So in order to do that, we'll be developing a feature set around in later releases that actually goes and inquires the exact path from the very routers. Now, I'm going back to my CLI, and I'm turning on another LSP. In this case, this LSP and this LSP, the definitions are similar, except the path profile is different. It's 21 here. So just a little more on the path profile. As I mentioned before, there's no significance on the PCC. However, on the NSP, what path profile translates, or 20 translates to, is instructions for the NSP to compute an Anycast pair paths using Anycast SIDs if possible. Similarly, on 21, with the name loose hop, we're instructing the NSP to compute a path based on the best node SID ERO for intermediate ASBRs. So once we go back to our demo there, and if I look at this LSP here, and if I overlay this LSP, you can see that I only have some of the border routers highlighted. So this is clear if I go into the 3D view, as you can see. The first LSP spans across Anycast, and the second LSP picks the best node SID to transit across the ASBRs. So these are particular options that we were talking about before with respect to computing interdomain connection paths. And all of these LSPs, while we're supplying from the CLI, I can also supply them from the NSP itself. So I can simply create a path name here. And I'm supplying the PCC address. Which is the destination there. So I'm traversing from right to left here, from the east domains to the west domain. And I'm going to specify my profile ID of 20. And submit. And you can see, going from the east to west domains, again, it picks the best Anycast pair to transit across the domains to the destination. So based on the video, as you can see, the NSP computes interdomain paths using the two options that I specified. One is a loose top Anycast, and the second option is a loose top node SID. So this is how NSP enables the operators to compute interdomain paths using any of these options as I described. And stay tuned for more videos on the interdomain connection points.